The following terms are useful in characterizing sinusoidal or trigonometric functions. The period, which is a measure of one complete cycle. Period, in this case, is defined as 2 pi over k, the horizontal stretch factor, or 360 degrees over k. The amplitude is a measure of the distance from the max and min to the central axis, and you can calculate amplitude in this way, max minus min divided by 2. Again, it's an absolute value or magnitude. Central axis is the equation of the line that runs through the middle of the sinusoidal wave, and you can determine the equation of the central axis by y is equal to max plus min divided by 2. And the phase shift is just basically a horizontal shift in the left or right direction. Combining all of those into one equation, we have y is equal to a, which stands for the amplitude, times the function sine, k being the horizontal stretch factor, x minus d, d being the phase shift, plus c, and c is basically the value of the central axis or the vertical shift right there. Okay. Same thing for the cos. A is the amplitude, k is the horizontal stretch factor, which relates to the period, d is the phase shift, which relates to a horizontal translation left to right, c represents the central axis, which is basically a shift up or down. We can certainly use mapping notation to transform a point, and these are basically your 5 basic points on the sine graph given to you in radians. And these are your 5 basic points on the cosine graph given to you in radians. So these are the maximums, the minimums, and the zeros of the functions. Okay. So if we take a look here, it says state the characteristics of the sinusoidal function y is equal to 3 sine bracket 2x minus pi over 3 plus 4. The first thing that you have to do is you have to factor out the 2 here, because we can see from the equation given to us previously the k value has to be factored out. So in factoring out the k value, we end up with y is equal to 3 sine 2x minus pi over 6 plus 4. We look at this value right here. That value represents our a value, so I know that the amplitude is 3. So amplitude is 3. This right here, the 2, that represents the k value, okay? And so I can calculate the period. So period is equal to 2 pi over k. In this case, it's 2 pi over 2 because my k value is 2, and so therefore the period is pi radians. If you wanted to do that in degrees, that would be period is equal to 360 over k, and then substituting k in is 2, so period would be 180 degrees. I look over here, this right here is my d value, or my phase shift value, and I have x minus pi over 6, so therefore I know that I have a phase shift pi over 6 radians, or 30 degrees to the right. Remember that when it's minus a value, it shifts to the right, but when it's plus a value, it shifts to the left. And then plus 4, that means that there's been a vertical shift 4 units up, and so therefore the central axis is defined as y is equal to c. 4 in this case is c, so the central axis is located at y is equal to 4. Just to review, I factored out the 2, then I identified what a, k, d, and c were, and used them to describe the characteristics of the function. We can also apply transformations and sketch a function using mapping notation. And in this case, as you can see, we'll be working in radians. So when I use mapping notation, the first thing I do is I look at the parent function. The parent function in this case is the cosine function. Y is equal to cos x. And then I'll write out the transformed function, 3 cos bracket 2 x plus pi over 2. And as you can see, there is no c value, so there was no vertical shift here. Then I write x and y, and I write how this is going to be transformed. So I have to remember that if my k value is 2, then that means I'm going to multiply all the x values by 1 over 2. And then since I have x plus pi over 2, that means a shift to the left. I subtract pi over 2 there. The amplitude affects the y value, so 3 times y, and again, I do not have a vertical shift, so I have no plus or minus value there. So it's just 3 times y. Remembering that I have characteristic points for the parent function, and I'll go back and show you where those are. Remember, these are the characteristic points of the cosine parent function, 0, 1, pi over 2, 0, pi negative 1. I'm going to take all these points right here and I'm going to recopy them underneath the parent function, as we can see over here. Okay, so I've written out all the basic points on the parent function y is equal to cos x, and now I'm going to use mapping notation to apply all the transformations. So I take this 0 here and I substitute it in here. 0 times 1 over 2, well that's 0 minus pi over 2, so this is negative pi over 2. And then 1 times 3 is 3. Okay. I continue to do that for the remainder of these points. I take the x value, substitute it in, apply this algorithm right here, and then find the transformed point. By substituting all the points on the original function into the transformations, I now have points on my transformed graph. So I can go ahead and plot these points. But what the first thing you might notice is, given the graph that I have here, these 2 points are not on this graphing space that has been provided. So I can't actually use these 2 points at all. I can, however, use the first point, 0, negative 3. Okay, well 0, negative 3 takes place right here. Pi over 4, 0 takes place over here. And pi over 2, 3 is right here. Okay, so it looks like I can just use 3 points. But that is sufficient because we know that this is a periodic function, which means that it has a pattern that repeats itself again and again. I can actually just go ahead and fill in the rest of these points right here, simply by following the pattern that repeats itself over the domain of the function. Not necessarily my best work right there. It should definitely be more curved, but nonetheless, I believe you get the point. Okay, just to recap, I took the parent function, wrote out all the points on the parent function, or the characteristic points on the parent function. I took the transformed function, wrote it in mapping notation, and applied the transformations to those characteristic base points on the parent function. Then I plotted them and created the graph.